All right, let's get into it. Today, we're going to trace the entire path your Go code takes from the moment you write it to the second it actually runs. This is the big picture, the 30,000-foot view of Go's architecture. And hey, this is just the beginning. We'll be diving deep into each of these stages in future explainers. So let's kick things off.
You know, it's a command every single one of us types probably dozens of times a day. But have you ever really stopped and wondered what's actually happening under the hood? Because it's not just some simple little command. No way. It's the starting pistol for this incredibly fascinating and highly optimized journey.
You know, the best way to picture this whole process is like a factory assembly line. It's really sophisticated. Your Go source code, that's the raw material going in one end. And what comes out the other? A single, ready-to-run, high-performance executable file. And this assembly line, well, it has three main stations. So first up, you've got the compiler, which forges your human-readable text into instructions a machine can actually understand. Then it moves on to the linker, which handles the final assembly, connecting all the different pieces. And last but not least, the runtime fires everything up and brings your code to life. That's our roadmap for this explainer.
Okay, let's zoom in on that first phase, the compiler. Its whole job is to take the Go code that you and I write and translate it into a language the computer's processor can execute directly. But it's not just a simple one-to-one translation. Oh no, it's way cooler than that. In fact, the Go compiler doesn't just translate your code, it puts it through a super rigorous 10-stage process. That's right, 10 stages of transformation and optimization, all designed to make your code as lean and fast as humanly possible. And here they are, the whole gauntlet. Now, I know, that looks like a lot, and don't worry, we're not going to dissect all 10 of these today. Honestly, each one deserves its own deep dive. But for now, let's just focus on two steps that have a massive, massive impact on your program's performance: escape analysis and SSA construction. So, escape analysis. This is all about being smart with memory. For every single variable in your program, the compiler has to make a critical decision. Can this variable live on the superfast temporary stack, or does it have to escape to the shared, more permanent heap? This single choice has huge implications for how fast your program runs. Think of it like this. The stack is like a temporary personal scratchpad for each Go routine. It's incredibly fast to write on and erase. The heap, on the other hand, is like a big shared whiteboard for everyone. It's more flexible, sure, but it's slower to access and needs the garbage collector to come along and clean it up later. So escape analysis tries to keep as much on that fast scratchpad as possible, which is a huge reason Go programs are so efficient.
Okay, the other step I wanted to touch on is turning the code into this special format called static single assignment, or just SSA. Now, this is some real compiler magic. It basically rewrites your code in a way that makes it way easier for the compiler to see optimization opportunities, like finding and completely removing code that will never ever be executed. We call that dead code elimination, and it's a key reason Go binaries are so lean and so fast.
All right, moving on to the next station on our assembly line, the linker. So once the compiler has done its thing and created these optimized instruction files, we call them object files, it's the linker's turn to step up and perform the final assembly. The linker is basically the master assembler. It takes the object file from your code, goes and grabs all the necessary bits and pieces from the Go runtime and any standard libraries you're using, and it stitches them all together into one beautiful self-contained executable file. But it does something else really important too. It adds some essential metadata. One of the most critical pieces of metadata the linker bakes in is this table called the PCLN tab. I know, it sounds super obscure, right? But what it is essentially a map. It's a map that connects the low-level machine instructions all the way back to the human-readable function names and line numbers in your original source code. So what, right? Why should you care about some internal metadata table with a funny name? Well, because without it, trying to debug or profile a Go program would be an absolute nightmare. So when is this map actually useful? Well, you know that super helpful stock trace you get when your program crashes? That's the PCLN tab at work. A panic that tells you exactly which line of code blew up? PCLN tab. That incredibly powerful pprof tool that lets you see exactly where your program is spending its time? You guessed it. It's all powered by the PCLN tab. It is the unsung hero of the Go developer experience for sure. Okay, so we've compiled our code, we've linked it, we have our executable file. Now for the final and most dynamic phase of all, the Go runtime. This is the environment that actually brings your program to life, runs it, and manages all of its resources. A great way to think about the Go runtime isn't as just another library. It's much more than that. It's like a tiny, highly specialized operating system that's bundled directly into your application. It's what handles all the cool stuff like concurrency, memory management, networking, the works. And inside this mini OS, there are three main control systems. I like to call them the power trio. You've got the scheduler, which is the absolute heart of Go's famous concurrency. Then you have the netpoller, which handles all your network I/O super efficiently. And of course, the garbage collector, which automatically manages memory so you don't have to.
The scheduler, in particular, is just a work of art. It uses this really clever model of Go routines, machine threads, and processors, the GMP model, and with it, it can efficiently juggle hundreds of thousands, sometimes even millions of concurrent tasks using just a tiny handful of actual operating system threads. It is, without a doubt, Go's concurrency superpower.
So let's pull it all back together now. The compiler, the linker, and the runtime, they aren't just separate tools that work in isolation. They are all meticulously designed to work together to create what is arguably Go's greatest feature. This entire assembly line, from start to finish, is engineered for one main goal: to turn your plain source text into a single, portable, high-performance binary file. A file that contains almost everything it needs to run, including its own incredible concurrency scheduler and its own memory manager. There are no complex dependencies to install, no need for a separate virtual machine, just one file. This quote just sums up the whole philosophy perfectly. Every single part of the tool chain, the compiler, the linker, the runtime, is designed with this one singular goal in mind, making it easy to create simple, self-contained, and incredibly powerful software.
So today, we've sketched out the map of this whole journey, from typing Go Run to seeing a live application. We've seen the major landmarks along the way: the compiler, the linker, and the runtime. The question now is, are you ready to explore the territory in a lot more detail with us? Subscribe to the Gokun channel for deep dives into Golang internals, architecture, and execution flow, advanced concepts rarely covered on YouTube, available for free.